Okay, let's talk about the model for a power system having many generators, not just 2 generators, like a single machine infinite bus system. So here we assume n buses and m generators in the system. So definitely n will be larger than m. Just give you some idea on how many generators buses to be modeled in the bulk power system. Like Eastern connection, usually the typical model has 70,000 buses. So n equals 70,000. For any buses, the voltage may be above 100 kV. So generators usually will be 10,000 or 20,000 generators. So each generator is modeled by the most detailed model with at least 6 orders, and also exciters model, governor models, KSS, and also there's could be some local controller like SVC, Stacom, capacitor bank, or other controller. So finally, the system can be huge, but now we want to just understand how to study the small signal stability for such large systems. So we start from a simplified model. By simplified model, because the small signal stability analysis itself is a simplified stability study. Okay, it utilizes linear system method to study a nonlinear system. So we can focus on the study analysis on the deviation around the equilibrium, so we can simplify a lot of things. So even I call it a simplified model, it can still be very accurate. It still can be the foundation for small signal stability study for any system. So which means the approach I'm going to talk about is still applied to even more complex system. So first, let's model generators and the loads. If the system has so many generators and some generators tend to become coherent groups, so we can treat each group as equivalent generator, modeled as just a equivalent machine. So because it is equivalent, a generator is not real generator, so you won't be able to give more details. So typically, such generators are modeled as classical models. So it's very easy to identify which generator can be from coherent group. If you have like data, very detailed power system model for Eastern connection, Western connection, or Tesla system, if you look into the model dynamic data, if you see many classical generators model, which typically means they're just equivalent generators for some coherent groups. You can either include damping or neglect damping. If you study transient stability, damping may not be that critical because you only just check how the angle can become stable, unstable after a transient period, after a couple of swings. But if you study small signal stability, you need to model damping. So basically, such generator can be modeled by the swing equations. For small signal stability study, we can, if you don't want to include how the governor can change the oscillation, you can assume the mechanical power to be constant, which means you just open the loop for the governor control without feedback. And you can somehow simplify the exciters as well. So we can just treat each machine as just a classical model. So there will be an internal EMF, which is the E prime. It's a transient voltage behind the transient residence. So we can neglect the armature resistance, and even we can ignore the saliency. We just treat every generator to be just classical model of a round generator. So we can also eliminate the variation in flux linkages. So the angle of the E prime will be the angle of the rotor. So we just treat them same. So we can model each generator by this single equation. So using this equation, you can calculate current and also power flow. All the loads can be treated as constant impedance loads. You only just need to utilize a single impedance or single admittance to the ground to model total load. So that impedance need to be calculated based on the nominal voltage and power. Then no matter it is dynamic or static load, you just keep using that single admittance at the load. Okay. I call it Y I0 because I just mean the index of the bus. 0 means ground. You just model the admittance to the ground. It can be calculated based on the power and the voltage. For the power network, first we need to construct the entire systems network. So this network include original transmission system, transmission lines, transformer, but also include what we have inside of each power plant, which is this one. Okay. We also need to add this branch with each generator to the network. So if you have M generators, so the final network will have N plus M nodes or N plus M buses. And we need to construct the admittance matrix. Admittance matrix need to include all the admittances between any two nodes or between any node to the ground. So we use Yij, just model a branch admittance between bus I and bus J. Okay, but if either bus is ground, so this one will become Yi0 or Yj0. They just model the admittance to the ground. So finally, we'll construct this extended network. So in the box will be original power network. And we have M generators, so each connect the EMF E prime to one bus in the network. So we'll add additional M branches and also additional M nodes. So then we need to construct the admittance matrix for the entire N plus M dimension system. If we use the ground as a reference, so we can write down the node voltage equations. So it will be a vector of a current from every bus, include the entry from every bus. And the Y bus is actually the N plus M times N plus M for the extended network. And V bus need to include the voltage at each bus and also the EMF, the E prime. If you forget how to build the admittance matrix, admittance matrix has the diagonal elements and off diagonal elements. Off diagonal elements simply just opposite of the actual admittance on the branch, and the diagonal elements is actually summation of all the branches connected to this bus, including the branch to the ground. So which means if you model each load as constant impedance or constant admittance, that one need to be added here. Definitely this Yi0 include the load, also include like some shunt capacitor. If you have a shunt capacitor at that point, so that shunt capacitor will add some what do you call susceptance to the admittance, add the imaginary part. Either add a positive imaginary part or negative imaginary part, depending on you connect a shunt capacitor or shunt writer. But load can also have real part, imaginary part, right? So finally, this Yi0 will include the load and shunt capacitors or writers, everything connecting this bus to the ground. Okay, so next we can simplify the network without sacrificing any accuracy. So the handling I'm introducing right now won't change any accuracy. It's accurate because we already make some strong assumption in this slide. Okay, so we have this node voltage equation, and if we spell out all the elements of each vector or matrix, we have N plus M linear equation. Okay, so you see we have from a V1 to Vn, which are the bus voltages of original network, and we have starting from N plus 1, we put E1 prime to En prime, which are the EMFs of the generators after the Vn. Similarly, we have from I1 to In will be the current injection from each bus, and the later one will be the current injection from the generators. And you can tell, so maybe this part will model the regional admittance system on the network, and there definitely will be other part will involve those ISD prime of each generator. But because finally, when you construct the admittance matrix, you have to, like for each element, you actually need to include all the branches connected to this one, including the generators. Okay, so that this corner, the block on this corner is not exactly the same of original admittance matrix, but you have to follow the same process to redo this entire Lie matrix. All right, so since we already modeled the generators also at buses or nodes in the network, so the injection from each power plant to the network will be from each the EMF. Okay, so right now there's no current injection on this part, so this one has to be 0. Is that clear? So if there's in the network, if there's a bus, that bus connected to a generator, so that generator will, that substation, that power plant will inject some current into the network. Because right now we model this generator, so that current, the same current must be from here, right, or from there. So they become the injection from the EMF, not become that injection from that substation, because we gave this branch to explain where this current is from. So which means original, this vector will be 0. So all the current injection will be from this vector. So we can utilize such information to simplify the entire matrix. We can assume there's a direct connection between any two EMFs. Okay, and using something like the Y delta transformation, you can somehow eliminate the center point. Like whenever you have 3 branches connected as the Y, so this Y can be eliminated by considering a delta connection. We can do such thing similarly, which is equivalent to eliminate many elements on the Y matrix to have a finally there's only one corner, smaller block, which is M times M. That one will model the connection, the equivalent connection between any two generator internal buses. Then we can get rid of the other element in the Y matrix. This one doesn't sacrifice any accuracy, basically because Y and delta connection, it's not like simplified transformation. It just keep all the information for the connection between any two EMFs. So for this one, we can assume the real part will be a Gij and imaginary part will be Bij. The Bij will model the susceptance between any two EMF, but Gij is explain the either resistance or conductance between any two EMF. So that basically G just model how the ID power is transferred from one generator to another, and B just explain how the reactive power is transferred. Okay, so now we can do such a reduction. So this is just the same equation. Just rewrite that equation in this matrix form. And next, it just gave us two equations based on these 2 lines. Okay, so we can eliminate Vn by using this formula, which is from the first equation. Okay, then we plug in this one into the second formula, then do some simplification. So we will have one equation without Vn. Because Vn is actually the voltage vector. So this is capital capital Vn. That's just vector for the original bus voltages on the network, and we eliminate those voltages. So we'll have this single equation. So this equation tells how the current is determined by those EMF vector. And the entire, this item in this bracket will be exactly the reduced admittance matrix. And this matrix is only n by n, m by m, not n plus m dimension. Okay, so now we can write the electric power of each machine. So electric power is taking real part of the EMF multiplied by the current conjugate value. Okay, and we take a real part, so it will need to utilize this reduced matrix. If you just plug in, do some simplification, you will get this expression. So the first item is each generator EMF square multiplied by GI. GI is actually the conductance from the EMF to the ground. So that is actually the load seen from each generator. It's total equivalent load you can see from each generator. So which means the first item just model some total load. Maybe the load is not exactly at the power plant, but which will be the total equivalent load you can see from each power plant. So that's a part of load the generator is supporting. And the next item will talking about the integration of the line flows from this generator to other generator. Okay, so here delta Ij is just the angle difference between any two rotor angle. So this is a very useful formula. Okay, we add this one to the swing equation of each generator. So now we will have the full differential equation for the entire system, right? Each generator has swing equation. In the swing equation, we have a PEI, which is the electric power of this generator. Then add this equation, we'll have the entire system. So now we have full system model, which is the first is still the angle deviation, which is equal to the speed. The second is equation, we replace PI by what we just derived. And also we assume maybe non-zero damping because we're going to study the small signal stability. So this model is very useful. It's not just for small signal stability, it's also very good for transient stability study. So we're going to use this model again in the next session. But now we need to linearize this model. We don't need the full model as a nonlinear system. So how to linearize this system? So we put the single machine feedback system, the linearized version on that corner just for the comparison. Okay, so we'll do similar thing. So we can somehow imagine, so when we linearize this, those equations, we'll still have this equation because that is unchanged. The second equation will involve some synchronizing torque and also some damping torque, right? And also some input. We're going to see similar things on this full system model. So here we assume there's an equilibrium point. And at that equilibrium point, each rotor angle will have delta I 0. So we use 0 to indicate the equilibrium. And for each nonlinear function like sine delta, cosine delta can be linearized up to the first order of a Taylor expansion. All right, so we'll directly get this one. So here, the KISIJ, which means the synchronizing coefficient between a generator I and a generator J. So this is just a first order derivative of the flow, which is back to angle deviation, so which is equal to this value. So if you compare this one to this one, they are very same, right? For single machine feedback system, the KIS is equal to the product of a 2 voltage magnitude divided by the total reactance and multiplied by some angle difference. So here is similar. Okay, and next we want to further simplify this equation because our goal is to have something like this one. So which means the left-hand side of the equation, we want to see the deviation, a derivative of all the state variable. Right-hand side will be a matrix, a square matrix multiplied by the state vector. Okay, so we only just need to divide the second equation both sides by 2h. So we just give it to all the other items on the right-hand side. So we can define alpha, beta, and u. So alpha here, so alpha basically here is just the synchronizing coefficients divided by the 2h. And beta is a damping coefficient. Actually, the di here, we call it damping, but actually it includes the damping of the generator and also include the frequency dependent load. Okay, so di divided by 2h will be beta. And we just make the delta Tm, which is the mechanical torque, mechanical power change. Yeah, I put delta Tm, it just make it be consistent with the single machine infinity bus system, but actually it's also equal to the delta Pm in per unit, the same thing. Divided by 2h, that will give you the input. Okay. All right, so there's one thing we can easily prove for all the alpha value. So if we fix I, but allow J to change from 1 to M for all the generators, so that one can be easily proved to be 0. The reason is 0 is really from the power flow equation, because from any bus, if you count the flow in and out from this bus to any other branch, if you add them together, that always can meet the power balance. So power balance, after linearized, you will get those key factors, because this come from the line flow. So that key factor divided by 2h will give you alpha. Then all the alpha value related to any bus for the rest of the system will be 0. Okay, so now we're ready to write down the state space the representation of the system, which will be, we're looking for this form of equation. So we can directly write down this state space representation. Okay, so the state vector will be all the delta angle deviations from first to the mth generator, and then we put the speed deviation at the bottom. Okay, and the A matrix will have this form. And input for this case, because we only assume the power change, mechanical power change, and that one is added to the differential equation of the speed. So we will see the input to be non-zero only for the lines regarding the speed. Okay. Let me ask the question. So what is the rank of this A matrix? So next step we're going to do will be similar to the single machine infinity bus system. And we're going to solve eigenvalues for this A matrix. The eigenvalues will have either real eigenvalue or maybe conjugate pairs of a complex eigenvalue. The conjugate pair of a complex eigenvalue, each pair will categorize some oscillatory modes. And if it has some real eigenvalue that indicate there's some modes for the entire system is moving together. That means a real eigenvalue. But how many non-zero eigenvalues does the system have? Do we know? Because here is the dimension is a 2m, right? Does the system have m pair of a complex eigenvalue, which means there's an m different way to oscillate, or it may have some real eigenvalue. If it has some real eigenvalue, all real eigenvalue non-zero. If it's 0, which means this matrix is singular. If it's singular, it may have at least one zero eigenvalue. It may have multiple. Okay, those are all the very critical issues determine how many modes we really need to study here. So the first question will be, what is the rank of this A matrix? The total dimension of the matrix is 2m, right?
Ideally, you would want the rank to also be 2m then.
We don't say ideally, we just based on what it is. I didn't give any number, just based on this structure. Can you imagine how many, what is the upper limit of the rank? The upper limit can be just 2m, okay? But if you can safely say, okay, no, I don't believe, so it's must be lower than this one, it can happen. That is actually related to this equation. Because what this one means, so if we fix the first index and by changing the second index, which is like we submit this row, it will be 0, right? Yes, if we submit this row, it will be 0. Similarly, we can submit every row, it will be 0, which means the first m columns are not linearly independent, they're linearly dependent. So the rank cannot be 2m. It's less or equal to 2m minus 1. So this is interesting. Okay, 2m is an even number. 2m minus 1 is an odd number. Odd number means they still have some pairs of eigenvalues which are oscillatory, but it must have at least one eigenvalue that is a real. Okay, and that will actually determine the stability of the system. The question will be, why that this system has 1, 0 eigenvalue? Because what 0 eigenvalue means is in certain direction of there's a certain eigenspace or eigenvector, right? That A matrix transforming the eigenvector is equal to 0. Okay. Sorry, it's a little bit over time, but let me finish this one quickly. So let's give you a real example. As for 3 machine system, okay, we start from those equations, linearized version of swing equations. By using those alpha and beta definition, we have this one. Find the eigenvector for lambda equals 0. So let's just put that eigenvector. Okay, first 3 elements 1, O1 equal. The last 3 elements O 0. So you multiply A by phi. Phi here is eigenvector, so you get 0. So this will be the eigenspace. In that space, the eigenvalue, which corresponds to eigenvalue to be 0. But what does that eigenspace mean? Each eigenspace means there's certain direction how for your state variable to vary. Okay. In that space, subspace, all the angle can change uniformly at the same speed, but frequency cannot change. So which indicate some condition, the frequency stay exactly at 60 Hertz, but angle together changing. Okay. That may be something interesting to transient stability, but not big deal for small signal stability. We really care about how those delta angle they oscillate near the equilibrium point. I really don't care if this point is moving together. Okay. If you want to find, I have homework questions. The homework question, I gave you this 3 machine system. You can solve this vector and tell me another eigenvector which correspond to that real eigenvalue. Okay, so finally, I gave you these 2 very useful conclusions. Our class next week will base on those conclusions. First of all, if you solve eigenvalue by solving that characteristic equations, it will have 1, 0 root, 1, 0 eigenvalue, 1 non-zero real eigenvalue, and 2 m minus 1 complex pairs, conjugate pairs of eigenvalue, which means the system, here's a typo, it's not n, but it's m minus 1, okay? It has m minus 1 oscillatory mode. So if the system has n machine, it only have m minus 1 oscillator mode. It's very easy to be understood because you can define any generator to be the reference. The other m minus 1 generator will oscillate relative to this one. You can arbitrarily pick anyone to be the reference for small signal stability study. So you don't have to study the m modes. You only just pick the complex ones. Okay. All right. Let me stop here. See you next Tuesday.